Hi. Before I jump into this one, I just wanted to mention something that I realized writing this up. This is I'm going in a new direction today. I haven't really done that terribly much this year. I did it a little bit, but just something worth pointing out that even this has been what 5, 6 years of teaching this course. Even now, I'm discovering new stuff. So hopefully, this puts a couple ideas in your head of something that might be interesting. It might not click in until like a year or two into college. I don't know, but for me, it's been a little while since college. So if it's clicking now, I guess you in the future might appreciate this. Hopefully. But let's get started. So, as I said, we're going to kind of expand into some new territory today. But in doing so, I made a realization that's going to hopefully point out a couple of shortcomings, not just of titrants, actually, a shortcoming of titrations, which was very interesting for me to stumble onto. I need to learn how to change my marker before I get started. So, first things first. The plan was to talk about Foss Forecast, Triprotic acids today. Phosphoric acid, I have the hypothetical titration curve shown. We are not measuring milliliters, so I'm not really concerned with the concentration of the acid. There are shown the relevant pK values. Obviously, pK1 shown 2.12, pK2 7.21, pK3. So that's the new part, pK3. Since there are 3 Kas, there are 3 equivalences. So the first reaction would be, oh, wow. Is it bad when I start writing like I can do subscripts later? H3PO4 would react to H2PO4 minus, that's the first, H2PO4 minus reacting to HPO4 2 minus, and HPO4 minus reacting to PO4 3 minus. So 4 species, 3 reactions. What we have here is this is like your starting species. This is your first intermediate, the second intermediate, and then the end point. And as you can see, we've got 1, 2, and there's your third equivalence up there. We're going to talk about that later, because that's where I determined there was a problem. But yeah, interestingly, or I guess not interestingly, as you might have guessed, the volume of base needed to add 1 equivalent of OH is half as much as the amount of base needed, the volume of base needed to deliver 2 equivalents. In other words, the volume of base needed to reach an equivalent is equal in each case. So if this was, say, 10 milliliters, then this would be another 10, and this would be another 10. This means that the math, expanding the math out from a diprotic system, should be relatively, if not straightforward, intuitive once you see it. So for the first 4 regions of our titration of hypothetical phosphoric acid, it's exactly the same as a diprotic system. For region 1, it's all H3PO4. And just like we did before, you considered this, even though it's a polyprotic acid, it's a polyprotic weak acid, we really only consider the first equivalence. So K1 equals x squared over F minus x. X is equal to the H plus concentration. So that's regions 0 and well, no, it's region 0. I'm not going to get ahead of myself. I planned it. I'm just suddenly I have something worth talking about. Not that the others aren't worth talking about, but I have something new to talk about, which I really like. Region 1, you're going to have a buffer, and the buffer is going to be using the first K. So we're going to have H2PO4 minus as the base and H3PO4 as the acid. For region 2, that's going to be our first equivalence point, which is our intermediate. So you know that the H plus value is equal to the square root of K1, K2, F prime plus K1, KW over K1 plus F prime. Again, don't forget that F prime is equal to our initial F times our initial volume over our new total, and that there's a dilution that's took place. For region 3, we now moved into our second buffer region, so pH is going to look very similar to region 1, except it's now different species. But, you know, if we're getting pretty good with this titration stuff, the species doesn't matter so much as understanding the math in terms of building our hypothetical titration curve. And then region 4. I lied. Region 4 looks different. Ha! I typed this wrong. But you know what? I can go through it anyway. We're gonna do it live. Region 4 for the diprotic system was our fully basic, so I guess I'll write that here. You know what? I'll write it down here. For a diprotic system, we would be using Kb1 is equal to x squared over F double prime minus x, where x equals the hydroxide ion concentration. But here in the triprotic system, this actually looks like, not maybe unsurprisingly, like our first equivalence point. It's just been shifted over by 1, which is similar to what we were talking about with triprotic systems as a whole, where the second intermediate is just a rehash of the first intermediate with different numbers. So in this case, we would say that the H plus concentration would be equal to the square root of K3 F double prime plus K2 KW over K2 plus F. For sufficiently large K2, sorry, I lost my train of thought for a second. Sorry, yes, I'm back on board now. Not K2. For sufficiently large F values, if K3 F double prime is greater than KW, that goes to 0. If K2 is sufficiently larger than F, that goes to 0. And then you remember that the pH of this ends up being roughly 1/2 times pK2 plus pK3. We've got 7.21 and 12.32, so that's going to be about 8.5. Does that make sense? No. 9.5? Does that make more sense? 10? No, I can't add. Hold on, I can do this. Don't put me on the spot. It's 19.5. There we go. 9.75. Now, is it going to be exactly that? No, because in this case, you know, K3F double prime is actually probably pretty close to KW. So we would actually go through the math and do the math. And again, K2 is probably pretty small compared to F. In fact, it's so small compared to F that Mr. Mulick made a mistake in his approximation. This is what happens when you put me on the spot. I was looking at it like, that doesn't make sense. That doesn't make sense. This is the one that goes to 0. That F double prime should be sufficiently larger than K2, which, yeah, it is, because like these are usually relatively concentrated. So my point is, you're going to see different values out of the second equivalence point for the diprotic system versus the triprotic system, because in the diprotic system, you're kind of out of H's. It's not an intermediate, you're done. It's the fully basic form. So moving on from there, there's now this region 5, which is completely different between a diprotic and a triprotic system. But once we see what it looks like and how it works, I mean, to think about it, I should have copied over a picture. Region 5 is here. Region 5 is a buffer region. It's just a buffer region using K3. And since it's a buffer region using K3, we just do the same thing that we did with the K1 and K2 buffer regions, except it's going to be a different ratio. I'm really glad I have this little eraser here. It helps so much. No, not the highlighter. There we go. So 2 hypothetical situations. If you think you can figure this one out without me, I encourage you to do so. You can hit the pause button. Please figure this out and make sure I'm doing it right, because I'm about to write numbers for math I did, and I really hope they're correct. But for 11, keep in mind that, so now we have real data, we need to figure out what our equivalence volumes are. Are we in between VE2 and VE3? I don't know. Let's figure it out. To find any equivalence volume, where this VB here is going to be our equivalence volume, because this is the formula for doing a monoprotic titration, so it's only going to consider ripping off the first stage, but then we can, you know, double it and triple it. So 0.1 molar times 15 equals 0.3 molar liters times VB, and I'm pretty sure if we do the math, we get VB equals 5 milliliters. So that means VE1 is 5, VE2 is 10, and VE3 is 15. So we're between 10 and 15. So yeah, I like that. Which means for the first one, pH equals 12.32 plus log of 1/4, which is equal to 11.718. And for the second one, the pH is going to be 12.32 plus log of 2.5 over 2.5, because we're in the middle again, 12.32. Whenever we're in between two equivalence points, pH equals pK, whatever K is appropriate for this relationship. So yeah. Moving on into region 6, this is where we're at the equivalence point. This should be this part should be the same as region 4 for the diprotic system. It's just the end of the titration. There are no more equivalences after this, which means we're in a 100%, in parentheses, phosphate solution. To figure out the concentration of the phosphate solution, that would be using KB1. Is going to be equal to x squared over f, you guessed right, triple prime minus x. So f triple prime in this case is going to, I like using the initial one because it's the numbers I have here. It's a 0.1 molar solution of phosphate. We started with 15 milliliters. We've added 15 milliliters of base. Oh, look at that. I picked some numbers so it worked out nicely. So KB1, don't forget that pKa3 plus pKb1 equals 14. So for the KB1, we're going to say 10 to the negative 1.68. Wow, that's relatively basic. That's pretty strong. And going through all of this, X is going to be equal to our hydroxide ion concentration, which is in fact equal to 0.0235 molar, and that's a pH of 12.37. Couple things here. One, that's the equivalence point, and the pH of the equivalence point is 0.05 units away from pK3. Two, that tells me that the solution is almost half associated. Like this, if anything, this is one of those cases where that F minus X not being an F that we used to do in AP chemistry, that's like really important to do here. And then moving on into region 7, which is the old region 5 with excess base, we do the same exact thing we would have done before, where we have our base and it's being diluted, but the amount that's being diluted is only the excess. So 15 milliliters goes towards the titration. There's 4 left over. We now have a total of 34 milliliters, and the hydroxide concentration is 0.0353 molar. This is where it really starts to point out, like the excess hydroxide is not really ton more concentrated than just what the base gave you. And that gives us a pH of 12.548, which is so interesting. Because I'm not going to lie, the graph on your left is a hypothetical graph. And even so, this isn't the end. There should be, like, that should be an uptick, in the middle of an uptick, and the graph should keep going. Now, in real life, when you actually titrate phosphoric acid with sodium hydroxide, you get something like the graph on the right, where that definitely 10 milliliters is your equivalence point, 20, that's an equivalence point. There's no equivalent. Like, if you were graphing that yourself and you were looking at the graph on the right, I would wager that most of you, if I didn't tell you anything about it, would say that that is a diprotic acid, and you just kind of over titrated and kept measuring pH because you enjoy using a pH probe. It turns out that depending on your situation, you're not going to see all the equivalence points that you should. Now, why is that though? And I want to dig in a little bit more to that graph and then talk a little bit about other graphs. And the reason is that the pKa is too large, and keeping in mind that 12.34 is the pK3. Well, pKw is only 14. So when you're reaching that level, phosphate, like the last, like monohydrogen phosphate and phosphate, that's comparably basic and acidic to water. When you reach that concentration, Kw is impacting in a negative way. Not because like everything's too dilute, it's because the pH is so extreme that Kw is actually getting stressed to the point of pushing back. So there's a couple ways to look at this, but to look just at the numbers they got here, keep in mind that we've added, if you're added 30 milliliters to 10 milliliters here, you've got a total of 40 milliliters of stuff. You go a little bit over, you've diluted, like, just to put some, I'm gonna stop drawing circles, just to put some context to it, let's say you never diluted anything. What's the maximum pH that you should be seeing with this base? Well, yeah, it's 13. The pH of 0.1 molar sodium hydroxide is 13. That represents like an ideal. I mean, are you going to see that pH? No, because even by the time you've reached that equivalence, you've diluted your hydroxide. If you add more hydroxide, you're never quite going to reach that 0.1 molar. It's asymptotic. So this graph will approach 13. But because of that, any pKa's greater than 10 won't show well, if at all. Now, what does that mean? I mean, like, does it mean you can't measure your solution? No, you can measure it, and you could even do the hypothetical calculations. Like, that's the most important part. But in the actual lab, what it means is that you have to think about what you're titrating. Hopefully you know what it is. But you think about what you're titrating, and that informs what your expected data is going to be. And that's really hopefully what this whole course is showing you, a comparison between expected data and actual data. So for a little bit more, there's two more things I want to talk about and then I'll be done. This is a graph of tyrosine. Tyrosine is an amino acid, it's got a side chain, and the side chain has an ammonia in it. And interestingly, pK2 and pK3 for tyrosine are quite close in value. This one's about 9 and this one's about 11. And I included the alpha graph on the left. And the reason I included the alpha graph on the left is that it really shows what we're talking about, why we're seeing what we're seeing. Keep in mind that at the first equivalence point, VE1, hypothetically, we said that was you calculate the pH by doing the intermediate. At VE1, we have 100% H2A. I guess minus, but I'm not going to worry about it. At VE2, we have 100% HA. And at VE3, we have 100% A3 minus. Well, here's the problem. So for the first equivalence, yeah, you get to 100 based on the graph, based on the K values. Like this pK is about 2, this one, like I said, is about 9, and this one's about 11. You get to this, and so that works really well. And so when you get an actual maximum of your intermediate, you get a really sharp peak like you're supposed to. But for VE2, where you should have 100% of the second intermediate, that's here. And you can see that that fraction doesn't actually reach 70%. So really in that solution, it's 70% the thing it's supposed to be, and the other 30% are two other species. And that's actually kind of buffering the situation. If pKa's are too close, they buffer the equivalence. And then you don't actually see good data. Now, obviously, for PK3, we have another problem where this solution, I think, is getting a little too close to the concentration of your titrant again. But this represents an interesting scenario where if you were to look at that graph, you'd say that's a monoprotic acid. And it's not. Now, I think for me, one of the things that would tip me off that it's not is that that slow climb after the equivalence point tells me that something's going on. It shouldn't be a slow climb. It should be up and flat. So that would be a big hint to me. The last thing I want to do is talk about aspartic acid. Look at the data, hit the pause button. What are we seeing? Again, it looks monoprotic. Which K is that? Which equivalence is that? Okay, so I asked the question. Hopefully you paused. I asked the question and then I realized there's an x-axis on the graph. It's the second one. But again, what we see is that at the first equivalence point, H2A minus H2A whatever, H2A neutral, isn't 100%. Wow. And since it's not 100%, you're not going to get a smooth curve. So hopefully in looking at your unknown, you can say, based on what I think is true and what I know about the PK values, the biggest difference is between 2 and 3. The difference between 1 and 2 is not large enough to see. And so you know, looking at this graph, that the jump you see is actually twice the equivalence volume. You have to take Ka values into account in analyzing polyprotic titrations. Now that is to say, it's not to say that it's impossible, it is to say you can do it all on paper. I'm just showing a situation where even on paper, if you did it, you might get numbers that are a little bit discrepant to what you expect, or this is a case where the numbers are going to point to something that you don't think is true or you don't know is true. So that hopefully this shines a little bit more light into why titration curves might look a little bit messier than you want them to in the lab or even on paper. Thanks for watching.